So this is Janet Hildreth, and this is homework number 3. And I had learning points pages 75 through 86. So the first learning point is talking about sampling with the sprinter analogy. So the book tries to explain the concept of sampling frequency using the analogy of taking pictures of a sprinter during a race. So essentially, the sprinter represents the part of the body being scanned by the MRI. The number of photographs you end up with equals your frequency matrix. The length of the race equals the amount of time that you have available to filling the data points within the frequency matrix. And it also represents your acquisition window, how much time you have to fill that matrix. And how many pictures taken per second represents your sampling frequency. So before you begin, you need to know how many photographs you must take in total, which essentially fills your frequency matrix, how many photographs per second your camera can take, which equals your sampling frequency, and how long the race is, or your acquisition window, how much time you have to fill that matrix. So if the sampling frequency is 1 photograph and the acquisition window or the race time is 10 seconds, then your matrix will be 10. So now breaking that back down into your sampling interval equals 1 over the 1 photograph per second, or 1 second. So now if your sampling frequency increases, then the sampling interval will decrease. So take it, if your camera would take a picture every 2 seconds rather than 1 second, the sampling interval would be half of what you could acquire 10 photographs in 5 seconds instead of 10 seconds. So how I like to think of it is this little old game that most of us grew up on called perfection. So here you have your matrix, and you've got to fill your matrix before the time runs out. And if you don't build yourself enough time, then you're not going to be able to fulfill the time that you have to get that matrix fill. And the same thing, if you take half of the pieces away and you cut the time in half, then you'll have enough time to fill that matrix. But if your matrix stays the same, it is built in to have enough time to fill it completely. On to our second learning point, the relationship between your echo time, receive bandwidth, and frequency matrix. Your receive bandwidth determines the range of frequencies we wish to digitize during the acquisition window and has the same numerical value as the sampling frequency when Nyquist principles are applied. Sampling frequency determines the number of data points acquired per second. The frequency matrix determines the number of data points, the frequency matrix determines the number of data points we must collect during the acquisition window. Your minimum echo time is affected by the duration of the acquisition window because the echo is usually centered within the middle of this window. So say that your camera, going back to the sprinter and camera analogy, say the camera is only capable of taking a picture every 2 seconds as opposed to every second, but you still need to fulfill the frequency matrix of 10 pictures. How can you accomplish this? One way is to make the race twice as long, so instead of taking 10 seconds, it would take 20 seconds. So moving this back over to the MRI applicable terminology, if your frequency matrix is 256, then you need 256 data points to be collected and stored during your time allowed. Your receive bandwidth is selected of 32 kilohertz. Then 32 kilohertz is also your sampling frequency. So 32,000 data points are collected per second. Since the sampling interval equals 1 over 32,000, which is your sampling frequency, then your sampling interval states that one data point is collected every 0.00003125 seconds. So in order to acquire 256 data points, the acquisition window must be 256 times 0.00003125 seconds, or 0.008 seconds, which is 8 milliseconds. So the frequency encoding gradient must be switched on for 8 milliseconds in order to ensure enough time to acquire 256 data points and a sampling frequency of 32 kilohertz. Now, if you cut your receive bandwidth in half to 16 kilohertz, your sampling frequency will also be cut in half to 16 kilohertz. So 16,000 data points are collected per second. However, if your acquisition window is still 8 milliseconds, then you can only have enough time to collect half the data points, 128. But your matrix still requires 256. So in order to get all your data points, you must double your acquisition window to 16 milliseconds. This in turn has a 4 millisecond increase to your echo time because the peak of the echo moves in order to occur within the middle of the longer acquisition window. So for example, a minimum echo time was 10 milliseconds with a bandwidth of 32 kilohertz and a frequency matrix of 256. Half the bandwidth now moved to 16 kilohertz. There's a minimum echo time would be 14 milliseconds because of that movement along the echo bandwidth. The same effect can be seen if you change your frequency matrix. If the matrix is doubled from 256 to 512, then 512 data points need to be collected and frequencies must be sampled 512 times during the acquisition window. If receive bandwidth remains at 32 kilohertz, then the acquisition window and the echo time would have to increase in order to be able to attain the required matrix data points. Moving on to the next learning point is your chest of drawers. So talking about K-space is how the data is collected and stored and then from there turned into an image. So your K-space can easily be thought as a chest of drawers. So the number of drawers, or if we go back to this perfection game, these lines can represent drawers. The number of drawers corresponds to the number of lines within the K-space that needs to be filled. The number of drawers also corresponds to your matrix that is selected. So if the matrix is 256, then the chest of drawers would have 256 drawers, or the matrix has 256 lines of K-space. Now, an important fact about K-space to remember is that it is very important to understand that your K-space is not your image. So spatially, the data stored in the location of the K-space does not correspond to the location on your image. For example, information of the top of the K-space does not mean that that is what's going to be at the top of your image. So, the data points that contain the information about the whole slice. And remember that K-space has specific characteristics that define how it is filled because of steep and shallow gradients as well as positive and negative polarity phase gradients. So your K-space is going to have positive data points towards the top and negative data points towards the bottom. And it will fill from center out in a linear motion typically. There are other ways to fill the K-space, but those are going to be discussed later. So thank you again for tuning in, Janet Hildreth, homework number 3.